just a few more examples of being able to evaluate an integral using U substitution for indefinite intervals. And then we're going to move on to definite intervals. So we have this x sine 2/3 x squared plus 2. A pretty obvious substitution would be 2/3 x squared plus 2. And the derivative is going to be our 4/3 x dx. And that's good because we have x, we have dx, but what we don't like is this 4/3. So what we're going to do is we're just going to multiply both sides by the reciprocal. And we're going to say 3/4 du, and that's going to cancel. So we're going to say 3/4 du is going to be equal to x dx. And now what we can do is we can substitute for x dx and also for u. And so our new integral is going to end up being the sine of u. And then instead of x dx, we're going to have 3/4 du. Of course, we can factor out the 3/4. So 3/4 integral of sine u du. And that's just going to be equal to negative 3/4. So remember, when you take an antiderivative of sine, it's a negative cosine. Right? And then finally, we're just going to back substitute for u. So our answer, negative 3/4 cosine of, I believe it was 2/3 x squared plus 2. Right? And we should have a constant of integration after this step right here. I neglected to put it in there. So if you forget it, just make sure you put it in at the end. Okay. All right. And of course, take the derivative to check. One final example, and this is a sneaky one, but a fairly easy one once you see the trick. We have sine of x cos to the 4th of x. Now, a lot of students see this and they start to shut down a little bit because they don't work with cosine to the 4th a lot. A way to think of this is to write this as sine of x cos of x quantity to the 4th power. And I think if you do that, it makes it pretty easy. I think everybody can see that the interior function of that 4th power is cos of x. Now be careful, we know the derivative of cos is negative sine x, but we don't want a negative. Right? So what we're going to do is we're just going to multiply both sides by -1. So negative du is going to be equal to sine x dx. And the good news is now we can substitute. I'm going to substitute for u, which is cos of x. And then wherever I see sine x dx, that's going to be our negative du. All right, so it's going to become the integral of u to the 4th times negative du. Right? I'm going to factor the negative in front of the integral. We're going to integrate. So we're just going to add 1, divide by the new exponent, plus c. And we're going to back substitute. Remember that u was the cosine of x. And so our answer is going to be the opposite of cos to the 5th of x over 5 plus c. Right? Or another way to write it would be negative 1/5 cos to the 5th of x plus c. Either way, they're both just as good, right? Since they're both the answer. All right, so those are all examples of definite intervals or indefinite intervals. But what about definite intervals? Well, same thing, except at the end, we're going to have to plug in some values, okay? Now, there's two different ways to evaluate the same problem, and I'm going to evaluate it both ways just to show you. Later on in your careers in calculus, it's probably easier to use the second technique, okay? So we're just going to do this problem 2 different ways, and we're going to get the same answer, hopefully. So I'm just copying and pasting this so we get set up. The 2 ways that you can try to evaluate is you can use these things called dummy variables. This is the technique I prefer, especially for higher level calculus when you start having x's and y's in the same integral. And it just makes it a little bit easier if you have to do a substitution. All right. The second method is to write in terms of the new variable. Okay, so you're going to write the bounds in terms of the new variable. Okay, now I'm going to show you both techniques. Okay, we're going to start with technique one, the dummy variable. All right, and I like this method a little bit better, but not saying that the other one's not bad or anything like that. All right, so we're going to do a U sub. So U is going to be equal to, I think everybody can see that it's going to be x to the third plus 1. This is a really nice one. The derivative just ends up being 3x squared dx, and that's perfect. All right, now, here's where we're going to use the dummy variables. All right, so let's just set up the integrand first. So we have x cubed plus 1, which is u. That's going to be for the fourth power, du. And what we're going to do is we're going to have these dummy variables, which I'm going to call a and b. Now, a and b are just real numbers. We don't know what they are, but they just hold the place, okay, until we get back. So now we're going to add 1 to the exponent and do the antiderivative. Notice that there's no plus c here. Why is there no plus c? Because it is a definite integral. All right, if it was indefinite, then we would need the plus c, but this time we don't because it's that definite interval. So let's just kind of wipe that out. All right, so just be careful with those nuances when you guys are taking your final examination. Now, what we're going to do is we're going to back substitute. Right, and when we back substitute, remember we said that u was x cubed plus 1. Right, so we're going to get x cubed plus 1 divided by 5. And now, instead of a and b, remember the original limits of integration were 0 and 1. And by the way, this is a fifth power in here. I just neglected to put it in there. All right, so just be careful with that. All right, make sure that you write your dummy variables, and then from here, you can just integrate and then back substitute in terms of the original. All right, now we're going to use our fundamental theorem of calculus. And remember the fundamental theorem of calculus said f at b minus f at a. All right, so we're just going to plug in the upper bound, plug in the lower bound, and subtract. So we're going to get the quantity of 1 cubed plus 1 to the fifth over 5 minus 0 cubed plus 1 to the fifth over 5. Now notice it doesn't wipe out with the 0, okay, because it's not a polynomial completely. All right, the original, it's a polynomial, but it does have that 0 in there. So strike that comment. It is a polynomial. This just winds up being 2 to the fifth, which is 32. Excuse me, not 35. So we get 32 over 5. And then this just becomes 1 to the fifth, which is 1/5. So we end up with 31/5. All right, now let's look at the other technique. All right, so this is technique 2. All right, and this is where we are going to write the bounds in terms of the new variable. All right, so we're going to do the exact same stuff that we started with. U is going to be equal to x cubed plus 1. Du is going to be 3x squared dx. That's perfect. Okay. Now, the limits of integration are going to be when x is equal to 0, that means that u is going to be equal to 0 cubed plus 1 or 1. When x is equal to 1, u is going to be equal to 1 cubed plus 1, which is 2. So now, this is your lower bound or your lower limit, and this is your upper bound on your integral. And so what we can do is now we can now rewrite the integral in terms of u. Right? Now, we have instead of 0 to 1, we're going to have from 1 to 2. And this is going to be u to the fourth, all right, just like we did before. So u is coming in here. And then instead of 3x squared dx, it's going to be du. Right? At this point, we just add 1, divide by the new exponent. And now we're going to have, we don't back substitute because we already have u in terms of, or we have the bounds in terms of u. So this is going to be 2 to the 5th over 5 minus 1 to the 5th over 5. And this is just going to be 32 fifths minus 1/5 or 31 fifths. All right, so two different ways to evaluate the exact same integral. Right? It's up to you which method you like better. I'm going to use this method, the dummy variable method, for all of the examples. All right, and that's again because I know when, for those of you that are going to take Calculus 3 or other multivariable sorts of subjects, then it might get a little bit confusing when you start to go back and try to plug in terms of the other variables. All right, so what might be good is to maybe practice one, okay, or two of these, such as this one, and then in the next video, I'll run through the solution to it.